Good afternoon, everyone. Welcome to our second lab on influence of intermolecular forces and physical properties. I hope by now everyone has his or lab kit, and we are ready to continue with our weekly experiment without any hindrance. I plan on um, collecting all the labs or receiving your data sheet by next week. I know most of you received your lab kit this past Monday or Tuesday. If you have not received your lab kit, please send me an email and I'll try to contact the company, see what's going on. We are lucky in the sense that 2045 and 1025 introduction to chemistry, there is a pack load with the company that pack order until July, and I'm wondering, my concern is what are we gonna do if the company ship the lab kit by end of July, almost towards the end of the semester? Probably they will have to work back to back in their lab experiment. But as far as we are concerned, we are in good shape. Everything, including whatever was for lab number one, I expect not later than next Wednesday. I'm just giving you room because I don't know. I didn't know by yesterday or even up to now if everybody has his or her lab kit. But nevertheless, if you didn't check your email account or the announcement section on the course, last night I posted two video recording of myself going through today's experiment, explaining what you'll be doing, explaining what the title is all about, and I am expecting you to also use other resources to supplement the data sheet. When I looked at the handout, it doesn't really have more information in terms of the literature and the background to give you a better understanding on intermolecular forces. It's not only for this. It's not only for this course, but you need to read extensively on intermolecular forces because I know down the line you will be tested on intermolecular forces. But the lab, all right, this lab number two is not oversimplified, but just it addresses the effect of intermolecular forces on properties of substances. I know you are aware of viscosity, all right? You know viscosity. You have seen that, syrup is more viscous than H2O. Why is syrup more viscous than H2O? It has to do with the intermolecular forces. And in particular, the type of substances you are to work with or you have worked with is H2O, all right, isopropyl alcohol, and the acetone or the nail polish, all right, or the nail polish. The essence is to determine the rate of evaporation, which is a function of uh, temperature, and there are two parts. All right, you will have to do the two parts. There is part one and part two. In part one, you will measure the rate of evaporation of the three substances. Real quick, I'm gonna show you. All right, real quick, I'm gonna show you the data sheet, what you will be doing in those parts, part A, part B. These are the things you will need. In case you didn't check, you should have, I know you have your cell phone, you should use the stopwatch on your cell phone to time the rate of evaporation. If you don't have, all right, please, you should have filter paper. You can get from Walmart. It should be porous, just to observe the water. Scissors, scattered, preferably distilled water. You can use distilled water. Acetone, nail polish remover will do well. And isopropyl alcohol. You can use any alcohol. If you don't get this alcohol, please use any alcohol. It will address the concept of effect of intermolecular forces as well. For rubber bands, I wouldn't really say, if you cannot find rubber band, you can use a scat tape. The purpose of the rubber band is to wrap your filter around. Once you cut to a square, you watch the YouTube feed. Once you got to square, the rubber band is to wrap around the tip of your thermometer. It should hold firm. I've done this experiment and I've seen that if you don't hold the filter paper so tight on the tip of the thermometer, chances are you'll just be recording the temperature of the temperature of the atmosphere, and it will not work. So you want the filter paper to hold on to, and that is why rubber band is, all right, rubber band is recommended because it will squeeze continuously. But scat tape, sometimes it may come out, but it's highly recommended you use the rubber band to hold on to the tip of the thermometer, all right? So that when you dip your thermometer in your substance, it should soak completely, and tip it on the side of the table. If you look at this diagram right here, this is where the filter paper with the rubber band wrapped around it. The purpose of this is you cannot just place on the table. For example, if we place this thermometer on the table, of course the surface will generate, or it might have some heat, and it will contribute to faster rate of evaporation of your substance at the tip or at the filter paper. So you want to suspend on the edge. And the purpose of this scat tape right here, all right, this scat tape right here is for taping this side right here. Don't say, where am I gonna use that? Maybe they don't explain to you, but this is what you will need to tape the thermometer on the edge, all right, on the edge. For part A, you'll just record the temperature after every 30 seconds or 0.5 minutes. It should be in minutes. So if this is my solution, I'll just have to, maybe as soon as you remove the thermometer of the substance, you press start on your stopwatch or on your stopwatch on your cell phone, and this is what you will do on the data sheet right here. Right here, 00, what is the temperature of your substance? This is for H2O, this is for isopropyl alcohol or any alcohol, and then acetone. And here is the temperature change. What is the temperature change? Could be wondering how the change will happen. What you will do is, let me just see if I can show you the plot. You can upload a graph of temperature versus time here, and please include the unit. So I'm gonna have the time here in minutes. You may put it in parentheses in minutes, minutes like that. And here is temperature, temperature in what? Temperature in degrees Celsius, degrees Celsius. You will see on your graph, it may look something like this, and then it's just gonna come down like that, and then it might go like this once you plot. This is the T max right here, T, and then max, and right here is the T minimum. Whatever you'll have a straight line, this is the T what? T minimum, T minimum. To get this right here, this is where you will find the T maximum. What will it correspond right here? This is what you will be reading on your graph. And please draw to scale, that the y-axis should be drawn to scale, all right? The x-axis should be drawn to scale to accommodate all the what? All the time frame. You'll record your temperature from 0 to whatever time you'll record. If it is 10 minutes, maybe one line will be 1 minute or whatever you'll have. So this is for each substance. What is the maximum for H2O? What is the maximum for isopropyl alcohol and acetone? That's all what you will do for part one. For part one. Any question on part one, please? Any question? Should be straightforward. Any question? If there is no question, we will move on to part two. What you will do in part two. So that's what you will do in part one. All right, is just measuring the temperature. And you're going to explain later on the influence or what type of intermolecular forces. So in part two is influence of intermolecular forces on surface tension. What is surface tension? You should read this, you should understand this. It's one of the properties of liquid substances. You may have seen the beading when you wax your car, all right? When you wax your car, or maybe you have seen a wax car, the beading of the water droplet, whenever you're washing your car, or if it rains, the speeding of a rain droplet on a wax surface, that has to do with the surface tension. And surface tension is the resistance of liquid to flow. And this is related to the intermolecular forces, In this part, you'll have to get a pen. So assuming that this is, I don't know if you can see, this is something like a pen, assuming that is a pen. And your substance with the droppers placed on the flat surface, and count how many drops you will, all right, how many drops you will place on the surface of a pen before it overflows onto your kitchen table or whatever you will be performing the experiment. You got to record the number of drops. You see here, this is the number of drops it will take before it overflow. You can read the direction on part two carefully using the droppers. All right, you should have the droppers in your kit and count how many drops. So you'll have for each one of them. You're gonna make observation. All right. You may have 3 pennies, or you can use, maybe for consistency, use the same penny all the time. Because if I say use 3 pennies, maybe 1 penny is rusted. All right. Or maybe 1 penny will have some temps and might affect the number of drops and the behavior of each substance on the surface. So be consistent and use the same penny. And remember, you'll have to do 3 trials, trial 1, trial 2, trial 3. So I'm gonna do trial 1 for H2O, trial 2 for H2O, and find the average. What I'll be looking at is calculation. Don't just put the number here and say, all right, he will take his calculator and find the average. Show me the calculation. You may attach an extra piece of paper to show how you arrive at what? At the average of your average for each substance. Don't just use the calculator or your computer to put in. Do the same thing for isopropyl. And what I want you to do is for part A, predicting the intermolecular forces. There is somewhere about the intermolecular forces here. Part A, Part 1A, intermolecular forces. You're gonna read the four types of intermolecular forces. There are four types of intermolecular forces. One, dipole-dipole. There is ion dipole. There is hydrogen bonding. All right. And then London dispersion forces. You may want to read your text, any text, or on Google, anywhere you can write your own notes until you understand what it's all about in all those four types of intermolecular forces. You should be able to explain. You should be able to understand and be able to predict what type of intermolecular force will exist in a substance. When we say intermolecular force, it does not mean only one molecule. That means within the molecules of that substance. For example, H2O, what type of intermolecular forces will be in there? I don't want to use what I have here, but I can use a different to illustrate what you will do in this side. I may want to, let me see if I can use hydrogen fluoride. Hydrogen fluoride. This is or hydrogen fluoride or hydrochromic acid. All right. This is a compound, and when you are looking at intermolecular forces, assume that you have two of any substance. So if you have two of these, if you have two of this, if you have two of this, and you have two of this, and say I have two of these right here, what will be the type of intermolecular force, predominant intermolecular force which will exist? At the outset, you are expected to have covered the concept of electronegativity. Electronegativity is the ability of a substance to attract electron toward itself in a covalent bond that is sharing of electron. So here, there is sharing of electron, that is valence electron. You know what valence electrons are. Valence electrons are electrons in the outermost shell, okay? So first, in this substance, I would like to find the number of valence electrons. So valence electrons is determined by looking at the periodic table, and if I look at hydrogen, these as 1, fluorine, these as 7, all right, 7. And if I add all of them, these 8 valence electron, 8 valence. These are electron on the outermost shell, the total number of electrons. So they didn't indicate here as valence, but total number of valence electrons. So what I'll do is right here, this is 8. I'm looking for valence electron, valence electron. So how do I draw the Lewis structure? There are sets of rules I gave you in the pre-recorded lecture. Please watch part A and part B. One is you have to find the total number of valence electron, and then you draw the skeleton of the molecule, making connection between the atoms, and understand that this line or this connection has two electrons, 2 electrons. So rule number 1, total valence electron, draw the skeleton. Rule number 3 is subtract the bonding electrons. We call these bonding electrons. Subtract the bonding electron from the total valence electron. So if I subtract 2, I'll remain with 6. I'll remain with 6. electrons remaining. Now, the remaining electrons in drawing the Lewis structure, the remaining electron is given to, if you have a central atom, is given to external. But for a linear molecule such as this, you give it to, all right, you give it to non-hydrogen. Hydrogen does not end up with 8, that the octet rule. Hydrogen only ends with 8. So these remaining 6, nothing remains. All right, you just leave it that way. So if you count the total number of valence electron here, we have 1, 2, 3, 4, that is 8 valence electron, 8 valence electrons. So with that, this is what I'm looking for, total valence electrons. So if I was to draw the structure, I'm just gonna change the lines to dots. All right, change the, and remember electrons are paired up. It should be clear. You see, you can see the dot. There is a structure for hydrogen fluoride, all right, hydrofluoric acid. This is what I'm looking for. You're gonna do the same thing for H2O. Now to answer the question here, whether it is polar or non-polar, whether it's polar or non-polar, electronegativity is the ability of an electron of an atom to attract shared electron toward itself. And as you move from left to right, this one increases. It increases from left to right, and then decrease as you go down the periodic table. Decrease, go down the periodic table. So fluorine is more electronegative than hydrogen, and the sharing of electron, the shared electron is closer to fluorine, and the shared electron here, shall have had my electron right there, is closer to fluorine. We say that this is partially negative. We say that this is partially positive. You don't have to show me this in your exercise, but I'm just showing you what is going on in polar or dipole. So if that is the case, this is positive. If I have another one, all right, if I have another one here, if I have another molecule here, the arrangement will be in such a way that we have another fluorine there. This is the arrangement. And here is positive, all right, negative terminal, positive terminal. And what I have here is there is a force of attraction between the two molecules. There is a force of attraction between the two molecules right here. And we call this dipole, all right, dipole, and then dash dipole force of attraction. It's one of the electrostatic force of attraction between two molecules. I explained to you in my pre-recorded lecture the other type of intermolecular forces. So if this is what I was working with, I'll say that polar bonds. How do I know that they are polar bonds? By looking at the electronegativity and say electron will be pulled towards. Doesn't really matter, okay? If I hook up two elements, where are the two elements lie on the periodic table? If they are not the same, then chances are the bond here, not this bond we are talking about, the bond within the molecule. Are there present bond in the molecule? Yes. Polar, you see this one now, a molecule, this is within the molecule. Polar, I'll say that yes, the molecule is polar. That means there is the localization of electron. Expected types of intermolecular forces. You see here, I have what? Types, that means it could be more than one. Remember, London dispersion forces is present in all substances. So I'm just gonna write here is London, all right, London dispersion, all right, dispersion, force of attraction. This is one of them, because it's present in all substances. And then here I'll say this is what? Because of this, I'll say this is dipole, dipole, dipole. This is what I'm looking for in the type of intermolecular forces. You do the same thing for H2O. I didn't do anything, but remember, okay, for organic molecule, there is no central atom, it's not linear. You know how to read the organic molecule. For example, propane, CH3, this is propane, CH3, 8, like that. These three right here, you start constructing the backbone of the molecule first. The three carbons and then are hooked up to each hydrogen on the other side. So this is hydrogen, that is hydrogen right there. This is hydrogen at the top. This is hydrogen below here. This is hydrogen below here. This is hydrogen, all right. And this is hydrogen, 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 hydrogen. So for linear, you see, three carbons. You're gonna see where the oxygen goes. If I look at this, 1, 2, 3, even acetane has 3 carbons, you got to see the connection in order to draw the Lewis structure. Use the periodic table to determine the total number of valence electrons. Total number of valence electrons. So that's what you'll do for part A, predicting the polarity and whether the bonds are polar, whether the molecule is polar or non-polar. Other than that, you should answer the post lab. I'll post a pre-lab for this so that you can get started doing right away. So by next week, I hope we will catch up so that weekly you will turn in the lab for that or pre-lab for that particular week. Sorry about the delay. As I said, there was a pack order with the company. I received mine yesterday. I received mine yesterday, and I'm gonna be also doing, running the experiment, make sure that everything is working well, and if need be, show some demonstration. What I have done is I will be pre-recording the lecture as well and posting on Canvas. In case you haven't got a chance to look at, I would like to show you all right, I'd like to show you, let me just erase this. I don't want to. Clutter the screen. I want to show you where I posted the lecture and where will be for each lab, which is arranged on Canvas according to weekly modules. You'll be looking at the weekly modules for our lab. All right, let's see where things are. When you go to the module for number 2, intermolecular forces, I do have part A, part B. These are pre-recorded lectures, which is basically what I went through. What I want to do is just try to be posting ahead of time. You can do at your own pace. Say, for example, if you had watched what is in there, you understand what's going on. Maybe over the weekend you have an extra time, you can complete the data sheet, the pre-lab or post-lab, and just you don't have to spend time as like today. You can just tune in for a little bit of information here and there. If I have general announcement or anything like that, but if you can understand what I'll be posting ahead of time, that will be fine. Other than that, I would like to just end here our discussion today and let you continue with the experiment. If you have any question, I'll be available to answer any question you may have. Any question? If you have not received your kit, please let me know. All right. Please send me an email right away so that we can intervene on your behalf that you need to ship the lab kit, because the semester is rolling and we don't want to lag behind. Other than that, that is it for today. I would like to end the lecture if no one has any question. If no one has any question, I'm gonna unmute. I will unmute everybody. If you have a question, please let me know. Anybody with a question?
No, sir.
All right, everything is good. Have a nice day, everyone. Please use the assignment folder on Canvas to turn in your work. In case you encounter any problem, you let me know. Some of you may have received something about activity recording or reporting or through the email. I took care of that this morning. It was supposed to be due Monday, but for some reason you receive an email, but it's taken care of. Don't worry about the email you received that it's going to affect your financial aid. Everything is in good shape. Thank you. Be safe. See you next week, same time.
Thanks. Have a good one.
You too. Thank you. Appreciate it.